Okay, let's begin. Last class before the break. We're going to cover some important ideas, but we're not going to be too serious about it. Most of the time, we're just going to be talking and you're going to be listening. What are you guys planning to do for Thanksgiving?
Sleep.
Sleep. Studying for calculus is the only correct answer. Of course I'm going to be studying calculus, Jhevon. That's what you're supposed to say. Okay. Just in case. You're right. If I gave you that on a test and you wrote sleep, wrong answer. Studying calculus, Jhevon. Okay. We're going to look at a new topic to kind of segue into the second portion of our class. You're like, well, the semester almost over. How are we going to the second portion just now? Well, it turns out that doing the first portion actually taught us a lot about the second portion, kind of in an underhanded manner, which is what we're going to start to realize pretty soon. So we actually did, believe it or not, cover a lot of the groundwork of what we will be talking about. But the segue is going to be called Antiderivatives. So I'm going to tell you about mathematical objects called antiderivatives, talk a little bit about why they're important, and then kind of go into the second topic, and we're going to realize that these guys are going to be very important for the next phase. So, antiderivative. F of x be a function. An antiderivative of f of x. It might not exist. Which I'll probably talk a little bit. On some theoretical level, it'll always exist, but there are times when, for all practical purposes, it's not going to exist. I'll probably talk about that in a little bit. If it exists, is another function. Customarily, we call this big f of x. So little f of x is some original function that we're looking at, and I want to talk about its antiderivative. I'm actually talking about some other function, such that if I differentiate the big F, I get the little f. That's called an antiderivative. So, let's do an example. An antiderivative of x squared is, how about you tell me? X cubed over 3. And that sounds like my help, so it just came in. Okay. X cubed over 3. How is that x cubed over 3? Well, if I look at this as the little f, then it turns out that the big F could be thought of as the function x cubed over 3. Why? Well, differentiate that using the power rule. The 3 is going to come down, it's going to kill that 3 in the denominator, and then I'm going to subtract 1 from the power to get a 2. So if I differentiate this guy, it will become that guy. That is the definition of an antiderivative. It's just some other function that if I differentiate it, I get the original function. So here was my original function. This is something that if I differentiate it, I get that. Right? So that thing is called an antiderivative. Now, the word "an" is very deliberate. It is not the antiderivative. There is actually no such thing. Antiderivatives are not unique. Can someone tell me another one? Something else when I differentiate, I'll get x squared. Yeah?
like x to the fourth would be x to the fifth over 5?
No, for x squared specifically. Yeah.
X squared plus a number, like any other.
If I differentiate x squared, I don't get x squared.
What do you mean by
Antiderivative. Something that if I differentiate it, I get x squared as the answer. That's not bad.
that one plus a number.
Yeah, this plus a number, like 5. That's also an antiderivative. X cubed over 3 plus 9, also an antiderivative. X cubed over 3 plus pi, also an antiderivative. Why? Because we know if you differentiate a constant, it just goes to 0, it goes away. So, in other words, in general, if we take x cubed over 3 plus, we can call it a c, the antiderivative of x squares, they'll all have this form. In this case, c was 0, but it doesn't have to be. If I differentiate a constant, it'll just disappear, and this, the first part here, is going to give me the x squared. So, i.e., antiderivatives are not unique. So, we've just found a very easy way to generate an infinite number of antiderivatives. Literally x cubed over 3 plus any real number is going to be an antiderivative of that. And so it seems kind of silly to think of all of these guys rather than just think of, oh, there's one class of functions that is the antiderivative of x squared. So that leads to this other definition. To avoid just silliness like that, suppose big F is the antiderivative of f of x and with no constant term. Right? So I found an antiderivative of this where it has no constant term. A guy with no constant terms, there's a potential dangling participle here. The guy with no constant terms I'm referring to is big. So suppose I found an antiderivative that has no constant term, then I can say big F of x plus c is a general antiderivative. So there's an idea of a general antiderivative, and oftentimes you kind of leave this word out. So usually when someone says antiderivative, they really mean the general one. It's implied that you know there could be a plus c hidden there. And in this case, big F of x is called the primitive and the c is called an arbitrary constant. Because it could be an arbitrary constant. Literally any constant I put there, it's actually going to work. So it's called an arbitrary constant. Sometimes for emphasis, we would say of integration. I'll talk about what the word integration means pretty soon. It's an arbitrary constant. So this will be the primitive function, the plus c. The c is called an arbitrary constant. So, the general antiderivative of x squared, as an example, cubed over 3 plus c. The x cubed over 3 part is going to be called the primitive. And the c part is going to be called the arbitrary constant. So that's the terminology that we're going to use. Also, why is it called the constant of integration? Because, and it will make sense why we use the word integration as opposed to something else. That will be made clear later, maybe next class. Integration is the process of finding an antiderivative. So we call the process integration. So the verb is integrate. So if I ask you the question, find an antiderivative of x squared, an equivalent question would be, instruction would be integrate x squared. I can say that phrase to you, and you should know that I mean find an antiderivative. They're interchangeable. Also, for this reason, sometimes an antiderivative is called an integral. Specifically, an indefinite integral. Now, we use the word indefinite because we don't really know definitely what this function is, because there's a plus c, which could be anything, which to determine what the c is for our situation, we would actually need more information. So until we get that information, we're not exactly sure which antiderivative we're talking about. So we're not definitely sure. We call it an indefinite integral. So I can say the indefinite integral of x squared is x cubed over 3 plus c. Right? So I can make that phrase. So whenever I say that, you'll know what I'm talking about. Another thing, it's very important in mathematics that when you want to do something, you look cool while doing it. So we're going to develop a notation that will replace this phrase. So just like how I didn't want to have to write out, the derivative of x squared is 2x. Like I didn't want to have to write that phrase out all the time. We come with a notation. d dx of x squared equals 2x. Or I can say if f of x equals x squared, f prime equals 2x. I can have a very short, concise equation to actually explain an idea of what I'm thinking. And so we can actually talk about the notation for this. Now, like the word integration, the notation that we use is going to become clear once I explain some other things to you. But the notation is the following. We have a very skinny, elongated S. There's a reason it's an S, and I'll tell you why it's an S before, but it's very elongated, very elaborate S. What I would do then is I would write the function beside this guy, and then I'll put a dx here. This dx is just like the differential of x, and you can think of him kind of as in the same role of dy dx. Where the dx at the bottom is telling you who the independent variable is. So you can write that symbol, and then you would write equals big F of x plus c. Right? So for example, I could say and this will mean, right, you can how you'd read it is the integral. You'd probably leave out the indefinite part the integral of x squared with respect to x. That's going to be important in Calc 3. For now, not so important. Just know that this should always be there. It is an important part of the notation. You'll realize why it's important in Calc 3. In Calc 1 and 2, you'll probably just put it there just to be formal, but it's actually going to matter what's there when you get to a higher level. So the indefinite integral of x squared is x cubed over 3 plus c. So whenever I write an equation that looks like this, I am just making that phrase. And what does that phrase even mean? Well, it means that x cubed over 3 plus c is the general antiderivative of x squared. Meaning if I differentiate this thing, I get that thing, right? And I can express that idea by writing this, right? So this thing means I want the antiderivative of this guy, the general antiderivative. Another way to say that is I want the integral of this guy, or I want to find the indefinite integral of this guy. These are all different phrases for the same idea, the same thing. So that's what this would actually mean. So here is the integral of f of x equals big F of x plus c, and dx, and now its notation identifies independent variable. It's always to the right or on top, right? So if let's maybe talk a little bit more about that. So how we use this notation, because looking cool while you're saying something is important, but equally important is you always want to sound like you know what you're talking about. You always want to write like you know what you're talking about. So let's just make sure we know how to actually write this down. Let's say I want to find this guy. I can write it like that. I could also put the dx on top. I can like almost like a multiplying thing. I cannot write it like this. See, when you write that like that, it's like you don't even know what you're saying, do you, right? It's like you're writing a sentence, you put the period in the front of the sentence. Like, no, the period goes at the end of the sentence, right? It kind of looks weird. So this, no. dx always on the right side or on top in most cases. So this, good. This, okay. And it's actually pretty common for you to see that. That, no. Right? That means you don't know what you're talking about. At least you don't look like you know what you're talking about. It's important to look like you know what you're talking about. Okay. So that's how we say find the antiderivative of f of x in a cool way. And there's a way to make sure you don't look like you're trying to be cool when you really don't, you're not, but you want to make sure you're writing it in the right way. So that's that. Now, some remarks. I want to start here. Remarks. To say the antiderivative of little f is big F, another way you can say it if you were on this side is to say the derivative of big F will give you little f, right? Which means within this phrase of finding antiderivatives, obviously there's a hidden derivative somewhere. The derivative just goes from the right side of the equation to the left side, right? So if you look at it going in this direction, if you want to move from this position to the right side of the equation, that's called integration. If you want to move from this position to that position, this is called differentiation, which is we've been spending a lot of our time on. Which kind of tells you that hidden in an integration, there's some implied differentiation, right? Like if I can find an antiderivative, it must mean that there was somehow I could have found a derivative. And basically what that means is, one, every derivative rule that we know can think of it as an antiderivative rule in reverse. So basically everything I tell you about derivatives, there's a way to reverse it. And every single individual rule that I've given you, there's a way to reverse it. So every time I told you a derivative rule, I was automatically telling you an antiderivative rule. And so I'm not going to have to derive a bunch of stuff here, because technically you already know everything that you need to know here, which is really weird, but it's true. Like I just literally, everything you need to know here, I already taught you in the reverse order, is pretty much what I'm trying to say. So, for example, if I wanted to find the antiderivative of cosine of x, what do you think that's going to be? Sine of x plus c. Well, how did you know that? Like, I didn't derive that for you. How did you know? Well, you had a rule, right? Since if I differentiate the sine of x, the answer was the cosine of x. So pretty much, derivative tells me how to get from sine to cosine. So if I want to go from cosine back to sine, what do I do? Well, I integrate. So me knowing that the derivative of this is that means the antiderivative of this is that, right? So every time I tell you this rule, if you look at it in the opposite way, I told you an antiderivative rule as well. Now, sometimes you might have to tweak this a little bit. So if I were to ask this question, what is that one? It's the negative. Now that little negative sign causes students a lot of trouble. A lot of time, they get into the, and why is that? Well, that's because if I take the derivative of the cosine, I get negative sine, right? Now a lot of people think of, oh, when you're differentiating the sine, there's a plus sign over here, so they kind of automatically think that integral of sine is positive cosine. That is something that I see all the time. Why does that happen? I can tell you exactly why it happens. Because people don't write down the rules exactly. They normally leave that part out, right? So they don't realize that the sine, S-I-G-N, is only positive if there's a ddx in front of it. Whereas if there's an integral sign in front of it, there's a negative sign, S-I-G-N. So you might have to tweak the rules a little bit. So of course here, to figure out what the sign would be, I'd have to multiply both sides by -1, and so there would be a negative cosine on this side if I only wanted to look at the antiderivative of the sine function. Okay? So every rule that you know, it was a rule in reverse. So the antiderivative of secant squared. Tangent. So what about the antiderivative of 1 over x? Now, this one is a little bit weird, but I did actually prove to you that the derivative of ln of absolute value of x was also 1 over x. And this one is far more general because it also allows your x's to be negative. So it was derived for you that the derivative of ln of absolute value of x is 1 over x. And it's more general than because in this rule, you're only allowed to pick positive x's, so you really only get half the graph, whereas in this rule, I'm allowed to pick both positives and negatives, so I can get the full graph. And so that's going to be important. So that's another thing people often forget. You should not forget it. The absolute values, very important. Also here, the sign, when you have an integral, very important. So yeah, pretty much all the derivatives I was telling you before, you can look at them backwards and you automatically know an antiderivative. Now, when the functions get more complicated, it's harder to play this game. And so there are a lot of techniques and formulas that we would come up with to make it easier to just reverse a derivative rule. But I can tell you that even with all these techniques, and we're going to learn one or two of them really, integration is going to be in general a lot harder than differentiation. So if you've been having trouble with derivatives, sorry to tell you, it's not going to get any better. It's going to get a lot worse, right? So when you're going to deal with integrals, which you're going to learn a lot about integration in Calc 2, that's where you really learn all a lot of the integration techniques and ideas and tricks and the tricks of the trade. You're going to realize that having an antiderivative is going to be a very difficult thing to actually come by in general, and the rules aren't going to be as straightforward. The rules for derivatives, super straightforward, at least compared to antiderivatives. And you can pretty much, if I write down anything, you can think of a way to differentiate it, right? So if I ask you e to the x squared, what is the derivative of that? 2x e to the x squared. What is the antiderivative of e to the x squared? Think of a function that when you differentiate it, e to the x squared is the answer. I'll save you the agony. Turns out this doesn't really have an answer. There is no primitive for this. I promise you, any function you can think of and differentiate it, you're not going to get that guy. There's no primitive in the elementary functions. Now remember what I told you the elementary functions were. Polynomials, rational functions, trig functions, exponentials, logarithms. I said trig. What did I mention?
Oh, right. Did you say rational?
I did say right. Polynomials, rationals, trig functions, radicals. That's the one I forgot. Radicals, trig functions, exponentials, logarithms. So these were the basic functions, and we thought of these like the building blocks, you know, the infinity stones of the mathematical universe. We build up our functions with pieces of these guys. So we can take these guys, we can multiply them, add them, divide them, take radicals, raise them to powers, do all sorts of things with them, and we can generate the entire array of functions that we know about. It turns out all these functions that we can create with those 6 things, none of them will actually give you e to the x squared if you differentiate it. Which means, for practical purposes, this is an impossible thing to do. Like, you're not going to be able to do that. Whereas, that concept with differentiation doesn't really exist. There's a way I can figure it out. I mean, you know what I mean? Like, you give me anything. E to anything, I just take the derivative of the power times the original function. Like, I know that. But if I just want to integrate e to anything, well, now we kind of have an issue, right? So integration in general, this idea of reversing, it doesn't always work out very nicely. Sometimes you can't work it out at all. So it's literally like there comes a point where, which unless you're a math major, you'll never actually get to this point. There comes a point where we just have to start making stuff up to talk about the answers to this. Just like when you get the square root of -1, they just made up the number I just so that they could call it something, and then they came up with complex numbers. Integration is going to have the same kind of idea. There are going to be times when you're looking at something that's, for all practical purposes, impossible to integrate. The rules just aren't there. They can't deal with it. So in general, it's going to be a challenging thing. So one, you need to know your derivative rules very well, because chances are, when you're doing integration, you're going to have to reverse something. So you're going to need to know your derivative rules forwards and backwards extremely well, which is why, try to drill it into you guys with all these quizzes and stuff and really be like, because eventually life gets harder, it gets more complicated. So let's talk about a few of these rules before we move on, some generalizations. So we talked about the antiderivative of x squared, but what about power functions in general? So there is something called, some important rules. I'm going to call these the basic rules. One of them is called the power rule. Now, like, didn't we already talk about the power rule? Yes, we spoke about the power rule for derivatives, but now I want to talk about the one for integration. So there's something called the power rule for integration. So we know the power rule for derivatives, or just the power rule. If someone says the power rule, they talk about power rule for derivatives. If you want to talk about the power rule for integration, you have to say the power rule for integration. So probably don't leave that for integration. So we know d dx of x to the n is n x to the n minus 1, right? We have that memorized, we all know that. Okay. What is the integral of x to the n? So, in other words, we have to think of a way to reverse this rule. So, when we took the derivative, what actually happened? We realized that when we're taking the derivative of x to the n, this gave us n x to the n minus 1. So notice here, this guy I can call the old power. This guy I can call the new power. How did I find the new power? Well, it was the old power minus 1. And you'll notice what we did here was we multiplied by the old power. So if I wanted to differentiate, what I did was I subtracted 1 from the power and multiplied by the old power. Reversing that process, what would that mean? Well, instead of subtracting 1 from the power, I'm going to add 1 to the power, right? And instead of multiplying by the old power, literally do the opposite. Divide by the new power. Now you're going to realize that if I plugged in n equals 2, I get the x cubed over 3, which we already know would work. That rule is actually how you do it in general. So this is called the power rule for integration. One important thing to note here is that your n has a restriction. It can't be negative 1. So as long as the power isn't negative 1, we will have that rule takes effect. So, example. Where I saw the integral of x squared. But if I ask the integral of x to the 5th, what is that? X to the 6 over 6 plus c. Integral of x to the 7th, let's do 12. X to the 13 over 13 plus c. Okay, integral of x to the pi. Integral of x to the square root of 2. Okay. It does not matter what the constant is, how ugly it looks. If you have x to a constant power, you add 1 to the power, divide by the new power, add a constant. This will work for every constant power except minus 1. So this is called the power rule for integration. What if n equals minus 1? Is it impossible? Well, if we have x to the minus 1, how would I do that? Right, that's the same as 1 over x. And we actually know what that is, right? ln of absolute x. So that is the second rule that you should know, the basic rule. How to integrate 1 over x. So your x cannot be 0, however it could be positive or negative. We consider this to be ln of the absolute value of x plus c. that?
E to x.
Right, we know that derivative of e to the x was e to the x. Or better, we can generalize this slightly, and where this rule comes from, we can justify it later, but you can probably see what the answer is going to be. E to the kx. K is a constant. What do you think that's going to be? Like e to the 3x, for example. What would the antiderivative be? Yeah, exactly.
E to the kx over k.
E to the kx over k. That's a nicer rule to remember. And also notice that this rule is contained in that rule because in here k is 1. So you just get the same as that. This is true in general. So for example, it's also important to know that k is a constant. Something like this does not work in general. It works if k is a constant, and that's an x. That form of the power is important. The only way this could change, you could do this as e to the kx plus a constant, and then it will still look like 1 over k e to the kx plus the constant. But other than that, I would not actually worry about it. I'd probably even prefer that you just factor off the e to the x plus the extra constant. So this form, very specific, so don't actually mix that up. So for example, if I had like e to the x squared, you should not think of that like e to the x times x and then put 1 over x e to the x squared. You notice that if you differentiate that, you wouldn't get the original. Right? So it has to be a constant times x. It's 1 over the constant e to the constant times x. Okay. So for example, if I had the integral of e to the 3x, that's 1 over 3 e to the 3x plus c. If I had the integral of e to the minus 2x, that's going to be minus 1 over 2 e to the minus 2x plus c. If I had e to the pi x, it's 1 over pi e to the pi x plus c. Right? So that's always going to be the rule. That's another basic rule. And for, I'll call this a category of basic rules. Basically, reverse if you know a derivative rule for a very specific function, I expect you to know the integral of that very specific result. So under this category, you will have things like the integral of cosine x is sine of x. The integral of sine of x dx is minus cosine of x plus c. Under this category, you would have the integral of secant squared of x dx is equal to tangent of x plus c. Under this category, you'll see that the integral of secant x times tangent x dx, that's equal to secant x plus c, because you should know that the derivative of secant is secant tangent. So pretty much if I tell you the derivative of this specific function is that specific result, I expect you to know that the antiderivative of that specific function is the previous guy. So pretty much everything that I told you about specific functions that are reversible, I'm going to expect you to just know that as a basic rule. So for you now, you're going to consider these things as the basic rules of integration. So the power rule is one of them. Being able to integrate 1 over x is one of them. being able to integrate an exponential is one of them, and pretty much the derivative rules of every specific function is an antiderivative rule in reverse. These are all what in your mind now is called a basic rule of integration. Now, why is that important? Like I said, integration in general is a very challenging thing. You're going to go into Calc 2. They're going to teach you a lot of different methods of integration. They will not be applied as clearly as the derivative rules from Calc 1. So you are going to look at an integral, and there's a lot of times there's going to be no clear way to proceed. It's not like in differentiation where, oh, if I see two functions multiplying, it's definitely the product rule. It's not the same with integration. You can have a product of things multiplying and the equivalent of the product rule won't work, right? The equivalent of the product rule for integration is called integration by parts. We'll probably talk about that. Or you might see something, oh, if you see a composite function, you might think, oh, I can differentiate that using the chain rule, right? The equivalent for the chain rule in the universe of integration is called integration by substitution. But it turns out that if you see a composite function and you want to integrate it, substitution won't always work. There's going to be a variety of things that can work, that might work sometimes, right? So it's a lot more sketchy, right? And so what you're going to want to do is there's going to be no hard and fast rule for doing any one particular integral. So you're just going to have a set of guidelines in your head for how to do integration. Here's how I would approach an integral. Here's what I would try first, or second, or third, or fourth. Because you don't really know. Kind of like with limits, how you don't really know. So you're like, well, let's try to plug in the number first. If that works, great. If not, I know I can try to simplify and do this. If that works, great. If not, I know I can look at the graph. If that works, great. If not, maybe I can use a special limit or the squeeze theorem, right? There's no hard and fast rule for how to do a limit, right? You just kind of approach it with a kind of guideline. You know there's certain things you try first, second, third. Integration is going to be the same way. There's going to be no hard and fast rule. It's kind of on a case-by-case basis. Now, to prevent that from being too confusing and too difficult for you, you should have a set of guidelines in your head. Now, one of the first guidelines, the first thing you're going to do when trying to approach any random integral is try to use a basic rule. That's step one, step zero, right? A random integral shows you, does this look like a basic rule, should be the first thing you ask yourself, which means you should know what the basic rules look like, right? If it looks like that, I already know how to do it. If it doesn't look like any of these, now I have to try something different, right? So basic rules for integration is all of this stuff, and you should just know them very well. You should know when you're looking at one, and you can just do it with a basic rule. So that's step zero. So step two would probably be integration by substitution. So if the basic rule doesn't work, you try, can I substitute something? Which we'll talk about substitution. But that's kind of the idea here. So yeah, this is step zero for doing any random integral. See if it looks like a basic rule. If it doesn't look like a basic rule, can I simplify it to look like a basic rule? Doesn't look like a basic rule, I can't do that. Then I think of something else. Maybe a substitution, maybe integration by parts, maybe something. And there's a list of steps that you want to go through. So first thing, know the basic rules. It's the first admonition, which means you automatically have to know all your derivative rules super well because you're going to have to reverse them sometimes and say them backwards. That's the first remark. Second remark. All right, so the first remark was all our derivative rules are automatically antiderivative rules in reverse. There are a set of rules that we call the basic ones. Unofficially, that's just what I call them. Oh, the basic rules. When I say basic rules, I'm talking about these guys. The kind of guys that you should just automatically know because you know the reverse. So that's the first thing. Another thing when it comes to antiderivatives is they're important, right? So I might be doing this and you might like, why do we care? Like why are we even doing this? Why are we just doing it backwards just to show off? Look, I can do this backwards. You know, like, is it like a moonwalk kind of party trick? No, it's actually an important thing to be able to do. There are problems where we need it. I will give you an example. Did I write it down? Okay, so this one's going to be a word problem, but I'm going to show you to work through it that we kind of need the integration idea. So that's the premise of the problem, right? A bunch of random calculus students, they grab Jhevon, they throw him off a cliff, right? Okay. The cliff is 500 feet tall. Okay, so they throw him off a 500-foot cliff. He's thrown with an initial velocity of 10 meters per second, feet per second. So, obviously a lot of animosity here. They didn't just like push him off the cliff, they literally threw him, right? They threw him like that, right? So here's the thing. You're seeing this, and instead of helping, you're like, I wonder how long it's going to take him to reach the bottom. Right? That's the thought. Like, I wonder, like, when is it all going to end? Okay. So, how can I track the position? When is the position going to be 0 feet from the ground? And we know that it is going to, that's it, right? No more quizzes, no more tests, no more nightmares. It's all over, okay? Now, here is what we know so far. This is clearly a problem that has like velocity and position in it. So we kind of start to think, okay, what do we know about velocity and position in terms of calculus? Well, we know that if S of t is a position function, we can talk about the velocity function, right? How do we get to the velocity function? The derivative, right? You take S prime of t. We could go even further. We can talk about the acceleration function. How did we do that? The derivative of velocity. That was v prime of t, or S double prime of t. So we know we can do that. In other words, to move down the list of these functions, if I have position, I can figure out velocity. And if I have velocity, I can figure out acceleration. How? By differentiation. But look at this question, though. Find the position, which means this first function that gets the process started, I don't know what that is. My ability to differentiate isn't going to help me here. Right? I need that to even start the differentiation process. Here, I don't have that. How am I going to actually solve this problem? How would I figure out the position? I just know his initial position, which means I know what the position function is at one coordinate. At time equals 0, position is 500, so I know that point on the position curve. And I know one point on the velocity curve. At time equals 0, velocity is 10. So I know that 0, 500 is on the position curve. I know that 0, 10 is on the velocity curve, but other than that, I don't really know anything. Or do I? So hold on for a second. So here's what's known, right? We know that this process exists, that we can cycle through these functions via differentiation in this order. Another thing that we know is acceleration. Now, unless Jhevon has a jetpack on his back, which we know he doesn't, we would know that the acceleration he'll experience will be the acceleration due to gravity. And that is something that they expect all science calculus students to know. What is that? 9.81. If we're looking in what units here?
32 feet. Oh, that's.
This is meters per second squared, right? Or, we're in America, so in feet it's 32 feet per second squared. And here we're measuring things in feet, so we use this. We tend to think of this as a negative because it's acting downwards, and we think of the negative, the downward direction as negative, right? So the acceleration due to gravity, you drop something, the Earth is going to pull that thing down and accelerate it at 32 feet per second. So in a vacuum, let's say there's no air resistance or anything slowing something down, if you drop something and it's falling, after 1 second, it will be traveling at 32 miles per hour, feet per second. So that is something that's also known. And it turns out that that's the entire acceleration function. I can think of this as a t. So it turns out, in this situation, the only function that I know in its entirety is the acceleration function. The acceleration he's going to experience is the acceleration due to gravity, right? So there's nothing speeding him up or slowing him down other than the Earth that's pulling him towards the floor. So the acceleration is the only thing I know. But I want position. So now you might think, if I know acceleration, how am I going to get up there? Well, now we know how to reverse the process. We now know that there is a way to go from here to go back up. That is called integration. So for a problem of this type, differentiation is not going to help me. In fact, I need the exact opposite. I need to go the other way. I know down here I want to get up there. Differentiation only tells me how to get down the ladder. I need to go up the ladder. Integration is how you go up the ladder. So what we know for sure is that. So let's actually use that to solve the problem. How are we going to find this position function? So this means A of t is minus 32. From this I can figure out the velocity. Well, the velocity, that's going to be the antiderivative of minus 32 dt. Remember, the d is always on the right? Right side. Okay. Now, what is the antiderivative of minus 32? Minus 32t. Right? Because t is my variable, as shown here. I'm thinking of the variable as being time. Now, if I differentiate minus 32t, I get minus 32 by the power rule. Plus a constant, right? Because there might have been a constant there. So I know that my velocity function looks like this. Now, that's an arbitrary constant, which means I don't really know what its velocity is, or do I? Well, I do know a point on this curve, right? Since v of 0 is equal to 10, right? We know that it was thrown off the cliff at 10 feet per second. This means that if I were to plug in 0 here, the result would be 10. This means that my c is 10. This means that my velocity function is actually minus 32t plus 10. That's the velocity function. Now, how am I going to get to position? Well, position, I know, would be the antiderivative of velocity. So now, I can do the rules for that. So, what is going to be the antiderivative of minus 32t?
Wait, no.
Huh?
Oh, wait. Never mind.
What?
Sorry.
Minus 16t squared plus 10t plus some constant. Now this constant, it's different from the previous one, but that's kind of known. You can think of this as a C1 and that's a C2, but you don't really have to express that. You know it's a different constant informally. So if I want to know its exact position function, how am I going to find that arbitrary constant? Because there's an infinite number of functions represented here. So now I just figure out, well, I know another point. I know the position at time equals 0 is 500. This means that if I were to go into this function and plug in t equals 0, that should give me 500. Well, that's going to mean C2 is 500. Which means, ultimately, the position function is this, plus 500. Which means, for example, if I wanted to know how long is it going to take him to reach the ground, right? How long will it take to get to position 0? What I just do is I set this equal to 0 and solve for t, right? Which is a quadratic function. That should be able to handle it, right? And notice what happened here is the antiderivative of t to the 1 is t squared over 2, and the over 2 cancels into the 32 to the 16. By the way, I don't think any of you are in physics, at least you probably shouldn't be, because I think calculus is a prereq for that. But when you go into physics class, general physics 1, not physics 207, I believe is the number. In chapter 1, you're going to talk about equations of motions, and they're going to give you a bunch of equations, and your professor may or may not tell you where those equations come from. This is where those equations come from, right? So every equation in chapter 1 is derived like this. They pretty much start out with acceleration, and they use integration and derived all these formulas. So if you show up in physics 1, you're getting a quiz or a test on chapter 1, and you forgot some of the formulas, you can literally derive them back, and it's not difficult to actually do it. But they're not going to tell you. So they'll tell you something like y equals minus at squared over 2 plus v naught t plus y naught. And you have to remember at squared. No, it's actually integration, right? So they started out with the acceleration function equals minus a. You integrate that, you get minus at plus a constant. You plug in 0 for t, you find that constant, that's going to be your initial velocity. Then, this is for the v of t. Then you integrate that to find the position. That's going to be minus at squared over 2 plus v naught t plus some other constant. Plug in t equals 0 gives you the initial position. So that's going to be your y0, right? So they're going to tell you this formula in your physics book. This is the formula for the law, for free fall or something like that. They'll tell you that formula. And where did it come from? It came from here. So it's a very important thing. Like the basis of physics is built on this. So it's not just a party trick. It's not just, oh, let's see if we can do this backwards. That'll be cool. No, we need it. Like we need to know how to do this. There are certain problems that we can't solve without being able to do differentiation in the reverse order. So that's the second requirement. Third remark. Now this one is the most surprising, and this is kind of why antiderivatives is needed for the next section of the class. It turns out that antiderivatives have a special connection to area. Area. Okay, that seems kind of strange. Let's do an illustration. Let's say I had some function f of x doing its thing. And for some reason, which I'll give you reasons later, I wanted to find the area under f of x on some interval. I want to know what is that area. Okay, this is going to be a goal. Now, I don't know how I'm going to actually figure that out, especially if my function has this very weird shape. It doesn't look like a straight line, so I can't use the area of a trapezoid. It's not horizontal, so I can't use the area of a rectangle. It has a very weird shape where I don't really know how to find the area. So here is what we're going to do. Pretend we could find a function which we'll call big A of x that gives the area under f of x, right? So pretend that I can actually, oh yeah, give me this function. I can find a formula that's going to give you the area if you want, right? So let's pretend that we could find it from a moving up to x, right? Because it's going to be a variable. So pretty much what I want to do is I want to set my x equals b so it stops here. So there's a formula that if my f of x is here, a is here, and my b might be out here, I can measure the area up to any point x using this formula. A of x is going to give me the area from this point up to that point. So let's pretend we could find a function that does this. I don't know if such a function exists. I don't know how I would even figure it out. But let's pretend that we could do it. What must this function behave like? Well, let's actually see what it must behave like. So here is something I'm going to set up to figure out how it must behave. Let me draw this a little bigger so you guys can kind of see the ideas that I'm talking about here. So here's what I'm going to do. I'm going to know that I hit some point x that I know I can measure the area under that function. Right, so the area here is given by a of x. Now, I'm going to say, what if I kept pushing that function further, right? Like my b was further to the right, and I want to keep inching this function forward until x hits b. So I'm going to push this function a little bit further, and I'm being very suggestive here, obviously, to a point further along called x plus h, right? So I want to push it a distance h further, right? And so now I can extend what this area covers. And what is going to actually measure the area from this point to that point? Well, a of x plus h, of course. Right? Because this function can measure the area. I don't know what that it exists. I just pretend something could do this. There's a way to find a function that could do this, right? So that would be the area all the way up here. Now, here is what we can do. I am going to look at this extra strip here. There's a point here where it hits this height is f of x. Notice that that part here will give me a rectangle. And on top of that, I can put another rectangle that hits this corner. H. So I can look at these two pieces here. And so now here's what we're going to do. Let's measure, so up to this point we know what the area is. I want to measure the extra area that I get by pushing this forward. Let's actually measure the area of this part here. That's what I want. Now, notice that this part here, I can measure the area by just taking the area of this rectangle, which I know how to do, that's an area of a rectangle. This part here, though, is kind of weird shaped, right? There's a curve on top, I don't really know how to. I'm going to call this the excess, right? So the area of this entire shaded region is going to be the area of this rectangle plus the excess stuff, like this excess stuff, which I really don't know what it's going to be. But here's something that I would know. So now the area of the right strip, that's going to be the area of the yellow rectangle plus the area of the excess let's focus on this part for a little bit. That's the area of the rectangle. I know I'll find that easy. That's what I'm going to. What would the area of the excess? How is that going to behave? So here's what we're going to do. Look at the area of the blue. Let R equals area of the blue rectangle, because I'm already using big A for something. So this is going to be, notice that R is going to look like, well what? The area of the rectangle is height times base, right? So the base here is h. What is the height? It's f of x plus h minus f of x. Times h. Interesting. Starting to look familiar, but it's not quite familiar. Notice here that if I take r divided by h, I will get f of x plus h minus f of x. And here's what I'm going to notice, which is going to come in handy later. As h approaches 0, what do you notice about r over h? R over h will also approach 0, right? How do I know? Because if h is getting close to 0, then f of x plus h is getting close to f of x. It's like me closing this window down. The blue point is just going to get closer to the yellow point. That's basically all I'm saying here, just in math speak. You have to look cool while you're saying it, right? So basically this is going to happen. If I take my r divided by h, it will approach 0. Notice what this means. For the excess portion, here's something that I can know for sure is going to happen to the excess portion. The excess portion is just a part of this rectangle, which means if the area of that rectangle is approaching 0, what is going to happen to the area of the excess? It will also approach 0. This means if I take the excess divided by h, it will also approach 0 as h approaches 0. So I know that fact. So here's what we're going to do. I'm going to plug these ideas into this general equation here. Okay? So that was just a side note. Right, so this is just a side note. What does the area of the right strip actually, what is that actually? Well, I know the area up to this point, and I know the area up to this point. If I just want to find this area, take this area minus that area. Makes sense? So over here, this would look like a of x plus h minus a of x. What is the area of the yellow rectangle? Well, the area of the yellow rectangle is going to be height times width. That is going to be f of x times h plus the area of the excess. Well, that's just the excess. I don't really know what that is. But here's what I can do. I can divide both sides by h. Why would you do that? Because I see something that I know how to do it. And that will give me here the excess over h. The way to take that part is very familiar. That is a difference quotient for the function a. And guess what happens if I let h approach 0 of a difference quotient with denominator h? What is going to happen? Well, as h approaches 0, the excess over h is going to go to 0. As h approaches 0 of f of x, what's going to happen? Well, nothing. There's no h there. So that just approaches f of x. What does this guy approach? Limit as h approaches 0 of a of x plus h minus a of x over h. Yeah? A prime. That is another way of writing the derivative. In other words, if I pretended that I could find such a function, how would it behave? The derivative of that function would be the original function I wanted to find the area of under. What this means is that a prime will actually equal to f of x. Another way to say that, a of x is, how can I talk about a of x in terms of to the left? Huh? It's the antiderivative. What? If I pretend I could find a formula for an area to give me the area under a curve on some interval, what must that formula be? It turns out it has to be an antiderivative of the function I was looking under in the first place. And that is the idea that made calculus calculus. That is why we have this class. That is why calculus is a thing. That is why there's something called the fundamental theorem of calculus. Someone noticed this. Somehow me taking a derivative is connected to the area under a function. Or more specifically, if I could reverse the derivative, I could figure out the area under some function. Let's look at another one, another specific case. Let's look at the example that we looked at when we were trying to develop the rate, to solve the rate problem. We looked at an object where x was time in hours. And you said, okay, starting at time equals 0, this object takes off, is traveling at constant speed, and we know that after 3 hours, the y, which is the distance in miles, was 150. Right? So we traveled 150 miles in 3 hours, moving at constant speed. And then I asked you guys, what is the slope of this line? And you're like, well, the slope of the line is going to be 50. And like, how would you interpret this number? Well, it's going to give us the velocity of the object. Right? So we actually did that. Okay, the slope is going to give us the velocity. So if we could find a way to find slope in general, we can figure out the velocity of stuff. And that's how we figured out what the derivative was. So we just found a way to find the slope in general, which is creating the equation of a tangent line. Now, here's something I want you to piece together. Notice that we know about the concept of a first derivative, a second derivative, a third derivative. So if we have a derivative of a function, we can think of that as a function itself that we can continue to take derivatives. Which means, if I want, so this is the distance function here. Or in other words, I can think of that as a position function. What if I look at the function that I get by taking its derivative? Let's say I wanted to look at the velocity function. which is the derivative of the distance function. What would the velocity function be?
Horizontal.
It would just be a horizontal line. It's traveling with constant speed. In fact, we know what speed it's traveling with. It's traveling at 50 miles per hour. Now, if I look at the area under that guy on the same time interval, what do you think the area is going to be? It's going to be 150, which is specifically exactly the distance that I traveled. So when guys like Newton and his teacher was investigating this idea, they were looking at planets in the solar system and talking about orbits and, can we predict where Jupiter is going to be in 3 months or whatever. They started noticing this, and they started tracking distances and the speed that the thing was moving at. And they started to notice, you know what, the area under this thing is always kind of telling me about the outputs of that thing. Like I can actually track one using the other. So somehow, if I can plot the derivative, and I look under the area of the derivative, it somehow tells me something about, well, now we have a name for this function, the antiderivative. The antiderivative, the area under the derivative, kind of tells me about the antiderivative. In other words, we kind of ended up in a situation where the area under V on some interval, specifically 0, 3, was equal to, well, the change in the position function on the interval. i.e., something that you would notice, and pretty much every example you would come up with, you would notice this fact, is that if I wanted to find the area under V, and we're going to have a nice notation for this pretty soon, if not next class, the class after. I can actually compute this by taking the output of the antiderivative at the final point minus the output of the antiderivative at the initial point. And it turns out that every time you kind of do this with a graph, even if this isn't a straight line, right? Every time you kind of do this and look on a specific interval, you're going to notice that this relationship is going to hold. And so that might suggest to you, is something like this true in general? Like, is that always going to be true? The fact that you can, every single example you can think of that's going to be true isn't good enough for math people. They need to, well, maybe there's an example that you didn't think of where it's not true, right? So that's not good enough for math people. But it's a very curious thing to always happen. And so we started thinking, is this true in general? There's no way that can be true in general. That's just too nice. That's too nice. And so ultimately now we start to become interested in this thing, right? So before, as I mentioned to you, there were two problems that calculus was meant to tackle. There was the rate problem and the area problem. And for a long time, centuries, millennia. These two things were studied separately, because who would think that area had anything to do with speed? Like that's, where we think that's a connection. That's kind of silly. So you have a bunch of people over here studying rates, they're developing derivatives, and they're talking about that kind of stuff. And you have a bunch of people over here figuring out how to do with areas. And then there came a point where there was a difficult problem to solve. We didn't know how to solve it, we didn't know how to talk about it, we didn't know anything. And we started slowly studying that topic, and then we started to realize, well, if I'm looking at the velocity of this thing, which we have a bunch of math over here talking about velocity, it's actually connected to the area of this thing, right? Which is, we have a bunch of math now talking about area, and so now we're like, hey, these two things are related somehow. What's the relationship? Let's figure it out. Oh, here's a relationship. Calculus. That's how calculus happened, right? So that is the third remark. Area and antiderivatives have a very special connection. And moreover, we kind of know what that connection is supposed to be by looking at examples like this. So empirically, by experimentation, by coming up with specific examples, we kind of know what that relationship should look like. The idea is, how do we know that's true in general? there's a statement that tells us that these two ideas that I just mentioned are true in general, and that statement is the fundamental theorem of calculus, which we are going to prove, by the way. So we're actually going to show that the things that I just showed you, they will always happen in general for any examples of functions that you can come up with. Theoretically, we can always actually make this kind of connection. And when you get to, well, currently it's Calc 4, but, which is Math 392, but they're actually getting rid of that. Pretty soon you'll be doing this in Calc 3. When you get to Calc 3, you're going to realize that this idea is a more fundamental idea, kind of connected to, like, just it's a part of reality. You're going to realize that relationships like this specific relationship exists in multiple dimensions. So if we're trying to do math in a 10-dimensional world, which according to string theory, there are like 13 dimensions or something, like a fact like this is still true in that world, right? So this is a relationship that's not only true for the little pictures that we're drawing on a blackboard in 2 and 3 dimensions, it will be true in multiple dimensions. And you kind of generalize this idea in that class, which currently is 392, but you're going to start doing it in 213 by the time you guys get there. So, yeah. Let's talk about in the last few minutes, I'm just going to start attacking the problem from the opposite direction. I'm just going to give you the setup. So now, we kind of find out a lot of things about the rate problems through derivatives. We can talk about velocity and all sorts of applications with derivatives. Now let's talk about attacking the area problem. So, we're going to look at how did we attack the problem of finding areas. And then we're going to get to a point where I'm going to show you, we're going to reach the one, and we're going to hit a wall, we're going to realize, hey, on the other side of that wall is the rate problem, right? So we're going to figure out stuff to do with areas, we're going to hit a point and it says, to go further, we have to cross this boundary. But crossing that boundary puts us in the land of derivatives. And then they're going to be like, oh, there must be a connection to area and derivative, right? But let's actually look at it from the other angle. So we're attacking a different problem now, but we're going to realize we're really attacking the same problem, just from a different point of view. The area problem. So, I mentioned this like first or second lecture again. The area problem is a very important problem that we needed to solve way on in civilization, and we actually figured out the solution like a long time ago. Centuries BC, we actually knew how to solve the area problem, right? We have records of Archimedes having solved the area problem. Archimedes knew about finding areas of irregular shapes. We figured out the area of a circle using the solution to the area problem. So these are things that we knew for a long time. But say the area problem is finding areas of irregular shapes. We know how to find the area of a rectangle, that's easy. And even triangles, which we use the area of a rectangle to figure that out. And then, like parallelograms, we use figuring out the area of triangles to figure that out. And then, once we figured that out, we could figure out the areas of circles because we pretty much slice up a circle into a bunch of pizza slices, rearrange them into a parallelogram, and then we can use the parallelogram form. That's kind of how we figured out a bunch of stuff. And so, if I had this irregular shape, how do I know how much space it takes up? Right? How much space does this take up? And area is probably not general enough. How much space something takes up is probably better, because you can actually generalize this idea to volume. That's what you're going to do in Calc 3. Right? Volume is really just a higher dimensional analog of area. Now, for a while, we needed to know these for very economic reasons. Pretty much a lot of things we invented is for that. You have a plot of land, government decides to charge you taxes on your land. Like, how are you charging me taxes? Well, based on how much land you own. How do you know how much land I own? Like, look at my plot of land. How do you know how much that is? Well, Archimedes figured it out. Like, I don't know. They probably figured it out before Archimedes, but that was the idea. How could you actually figure out how much space someone has on their plot of land in order for you to charge them property taxes? Well, we knew the answer a long time ago. Solution to the area problem. Let me just tell you. One. Cut up the shape into smaller shapes. That you know the area of. Right? So you have this thing. I don't know how to find the area of that, but I do know how to find the area of a rectangle. Slice it up into a bunch of rectangles. Then, 2, add the areas of all the smaller shapes. The more you can do this, the better your approximation. So, I would kind of like guess, okay, this is maybe like 1/5 of the area of this rectangle, so I guess that. But if I wanted to find that even better, I could slice these things up into smaller rectangles. And there are ways to make this more efficient. I mean, you could start with a bigger shape, and then dissect this one into smaller shapes. And then keep dissecting further. And yeah, Archimedes was all about that. Legend has it, he actually was killed by a Roman soldier when he was actually, in the middle of a problem like this. Hey, move, get out of the street, old man. No, I have to find the answer. All right, and that's kind of how he met his end. Right, so he was obsessed with finding areas of stuff and just dicing them up. But as you can see, that, as you can probably tell, not very efficient. You don't want to hire a bunch of people who are just going to be 1, 2, 3, 4, like that's their job, right? So the idea is, can we make this more efficient? Can we formalize this idea? How can we get to a theoretical point of adding up a bunch of stuff? So the idea is now to find the area problem, to find a really nice solution to the area problem, we need to find a really nice way to add up a bunch of stuff. And that's where we'll pick up the next one. We're going to learn how to add things like a sophisticated civilization should be able to add things, not by counting a bunch of silly shapes. We're going to do it very efficiently. So enjoy your Thanksgiving. I know you guys will all be studying calculus over the break, so I'll also post some new homework for you guys to do. And I will see you guys on Monday. Huh? Quiz on Monday, yes. I'll also send you what that's about.